Okay, so I am taking like this is a combined class, so this topic is for grade 6 onwards. Okay, and students from any grade, I mean, of course, from grade 6 onwards who are interested are welcome to attend this class. I am following this grade, you can say grade 8 book, but the topic is the same. Even grade 6 is doing diffusion and Brownian motion. So the topic is the same and it's very easy, and there is nothing that is out of course. Okay, there is nothing that you will not be able to understand. So sixth graders will also be able to understand. Okay, hopefully. And if there is anything unclear, please let me know. But again, I think the stuff is the same, the topic is the same. Okay, that being said, so let's get started. uh, we will start with the kinetic model of matter. Kinetic model of matter. Now, this question is for grade 7 onwards, because grade 6 are newcomers. This topic might be new for them, but I expect grade 7, 8, and 9 students to be able to answer this. What is the kinetic model of matter? Just give me, like key points, summary. What do you understand by kinetic model of matter? Yes, Sarah, Ajwa, come on, this is easy. Just a recap. Quick, don't waste time. Come on, somebody raise hand. Ajwa, come on. Fatma. Sarah, I'm sure Sarah can answer this. Yes, Sarah? Come on. Kinetic model of matter. Yes,
Miss,
Ajwa.
I don't know the exact definition, but it's
No,
like
it's not
probably
a definition. It's not a definition. What does it, what does the theory suggest? Yes? Whatever you know, whatever you can understand.
that the molecules move from a higher concentration.
That's the definition of diffusion. Okay, Ajwa? Yes, Ajwa?
Matter is made up of several molecules like atoms.
Okay. Is that it? So see, here we are, all the grades together. Okay, all the grades together. It doesn't really matter which grade you belong to. We all need to learn this. Yes, Fatima?
Miss, the particles in a matter are always moving.
Okay. Yes, that's good. That's 1 point. Very good. Yes, that's correct. And? Okay. Okay. So see, when I suggest to students that, don't think that you are in grade 9 and you should not be attending grade 6, because I have seen many grade 9 students raising their eyebrows. Why should I attend grade 6 class? But when I ask them a grade 6 question, they're not able to answer. So the thing is, you should stop attending a class only if you think you can teach them. If you are good enough to teach them, fine, don't attend the class. But if you think you cannot teach them, then you should attend the class. That's my suggestion. Okay, I make my 9th grade daughter attend grade 6 classes. All the grade 6 classes that I have taken are attended by my grade 9 daughter. Because you see, I tell her, if you think you know everything, then you better teach. Okay, so kinetic model of matter, and I don't want you guys to forget this again. Okay, kinetic model of matter has 4 main points. Let me write them. Let me show them. I made this. These are the 4 important points in the kinetic model of matter. Remember this. This is so frequently asked in the exam. First of all, yes, Ajwa, I think Ajwa said that all the substances are made up of, she said molecules, but I would rather say particles because not all the substances are made up of molecules. Some are made up of atoms, others are made up of ions, and so on and so forth. So I'm using the general term particles, which can be molecules, atoms. So everything is included in particles. Particles are the smallest, smallest particle of which a substance is made up of. It can be molecule, it can be an atom, or it can even be an ion. Okay, and they are all the time constant random motion. Constant random motion. These are key words. Constant meaning all the time. They never stop. Random meaning in all the directions. No one particular direction, all the directions. The movement and the arrangement of particles is different in the three states. Okay, I just wrote down in a short form. This is shorthand writing. Okay, movement, arrangement of particles is different in the three states. Okay, and we will discuss how they are different. Okay, fourth is the pressure of a gas is due to particles hitting the wall of the container. These are the 4 points which constitute the kinetic model of matter. First of all, let's recap. All the substances are made up of small particles, be they solid, liquid, or gas. They're all the time in constant random motion. Movement and arrangement of particles is different in the three states. Pressure of a gas is due to particles hitting the walls of a container. Okay, you understand that? So let's talk about this. Now again, my question. Now this time the question is for everybody, even for grade 6 students. Can anybody really quick, in summarized form, concise way, tell me the arrangement of particles in the three states? So talk about arrangement. Okay, I do allow, I have now allowed students to attend my class, with whatever ID they want, but I would prefer if they use the same ID that I gave them. I would like that a lot, but I do allow students who are not using that same ID. But I don't like students, using fake names. That is still not allowed. Like anonymous, I don't like this anonymous. So either you change or I will remove you. Okay. Yeah. Okay. So okay, I can see Sabiha's hand raised. Okay, yes, Sabiha.
The movement of the particles in solid, they vibrate in the arrangement. They're packed together closely.
Very good.
In the move of liquids movement, they can move a little bit, but not a lot. And the arrangement of liquid is that they're close together, but they can move.
They can glide over each other. They can slide past each other, right?
Yes, they can slide past each other. And in the gas, the movement, they can move randomly, freely everywhere, and there's no arrangement.
Right. So there is no arrangement in liquids and gases, but yes, there is a regular arrangement in solids. They have rows and columns or different patterns of arrangement. Okay, there are different patterns of arrangement. Like in crystalline structures, they have really amazing patterns of arrangement, right? Okay, so that's good. Sabiha, you did a good job. I'm happy. You're a 6th grader and you did a fabulous job. Also remember that the particles of solid, they vibrate around their fixed positions, meaning they do vibrate, but then they come back to their original position. And so their original position stays unchanged. Okay, and I'll show you a video in a while. Okay, now tell me the definition of diffusion. Now tell me the definition of diffusion.
Miss, can I tell, please?
Please raise your hand. Raise your hand. Yes, I will give you a chance, but please raise your hand. Yes?
Miss, I'm new to Zoom, so I don't know how to raise hand.
No, it's okay. There are options at the bottom. Please explore them. Okay, go ahead and tell me the definition. Yes?
Miss, me?
Yes.
Miss, diffusion is the movement of particles from an area of higher concentration to lower concentration.
Very good. Yes. Very good. Okay. Can you? Yes. So that's right. So diffusion is the movement of particles from a region of high concentration to a region of low concentration. But I would like if you use the word spontaneous as well. It is a spontaneous movement of particles from a region of high concentration to a region of low concentration. What do you understand by spontaneous? What do you mean by spontaneous? Anybody wants to guess? Yes, Sidra?
Spontaneous
Come
means
closer.
with no external energy
With-
acting
Yes.
on it,
Yes.
like itself.
Yes. No external force. Yes, Abdul Rahman Saqib?
Miss, it means by not losing energy but doing the same thing again and again.
No, but not. No, you said by not losing energy. That's not correct. By meaning to say that no external force. For example, let me give you an example.
Like stern.
Yeah, like for example, if for example you add sugar into water and then you stir it, and because of your stirring it got mixed, is that diffusion? No, that's not diffusion, because you were stirring, so you exerted an external force. So therefore that is not diffusion. It would have been diffusion if you had not stirred and it had still dissolved. Then it would have dissolved due to its own motion, due to the motion of the particles themselves. So that would be diffusion. So remember, diffusion is the spontaneous movement of the particles. Now, why do you think the particles need to move from a region of high concentration to a region of low concentration? Why? Yes, Mariam?
So
Yes.
they can spread out evenly.
Okay, so why do they feel the need to spread out evenly?
Because one area might have high concentration and the other area might have low concentration.
Okay, but still, why? My why is still there. Yes, Sidra, you want to say
Because
something?
it's like if you have two rooms, if one room has a lot of people and that room is locked, but you know still that there is another empty room there. So when you'll open the door, all of the people will rush to the new room because they're too close together. And so there's
Okay, but still my why is still there. My why is still there. See, the thing is, remember, nature tries to balance out. Nature always tries to balance out. So when you have a lot of something in one region and you have nothing of it in another region, that if there is no partition, if there is no force stopping the particles from moving, they will try to balance out. That's the habit of, I mean, that's the, that's how nature works. Okay, it balances out. So if opportunity is provided, the particles will move to make sure that all the space is occupied. All the space is evenly, I mean, the particles are evenly distributed throughout the space which is available to them. Okay, now diffusion takes place in which states of matter? Which of the three states of matter? Yes, Javeria wants to answer. Yes, Javeria?
It happens in the liquids and the gas.
Okay, why? Why not solids?
Because the solids cannot move constant. They cannot have a very don't have a a movement that's able to have diffusion.
Yes, you are correct. So, okay, but I'm looking for a keyword. Why are they not able to move?
Well, because they're packed together.
Yeah, why are they packed? Because
Because they have to maintain a proper shape.
Because of the intermolecular forces.
yes, thank you very much. Okay, Aisha, I want to give you a chance. Yes, Aisha?
Because
But
the particles are tightly packed and they can't move, so the substance cannot diffuse into it.
yeah, talk about the intramolecular forces. Say that the intramolecular forces are so strong that they don't allow the particles to go too far. Okay, the intramolecular forces of attraction are too strong. They are like ropes which are holding the particles together, and they don't allow the particles to leave their position. So they cannot move. And if they cannot move, there will be no diffusion. Because for diffusion to take place, there should be spontaneous movement of particles, meaning the position of the particles should change. Okay, and that is only possible in fluids. And fluid meaning, what does fluid mean? Who will tell me?
The ability to flow.
Yes, ability to flow. Yes. Yes, Doris? What does fluid mean?
Substances that are available to flow,
Very-
like carbon dioxide or water.
Any gas or liquid. Okay. All the gases and liquids can be called fluids because they can flow, right? Okay. Very good, Doris. Okay, so that is so the diffusion can only take place in fluids. Now, why the reason why diffusion can take place in liquids and gases is because the intramolecular forces are weak, and so the particles can move. Okay, they can move. So will the diffusion be faster in liquids or gases, and why?
You can add that?
Yes, beta.
It will be in gases.
It will be faster in gases.
Yes.
Okay, now explain me
Because
why.
gases have more or less that internal force.
They have more or less force.
They have less internal
Yes.
force.
So you will say they have you won't use the word less. You will say that they have weaker intramolecular attractions. Okay.
Okay.
Yeah, you will say that the intramolecular attraction is weaker in liquids, and so diffusion will take place, but it will be slower. It will be faster in gases because in gases, there are no intramolecular forces at all. So there is no restriction on the gas particles. They are free. They can move wherever they want to go. They can go wherever they want to go. So the gas particles, they are free. There are no ropes attached to them. So they can go wherever, Okay? Gas particles are free to move. So therefore, they will move wherever they can, and therefore the rate of diffusion will be faster in gases. Okay. Okay. Now, okay. Can anybody explain me the effect of heat on the arrangement of these particles that Sabiha just explained us in solid, liquid, and gases? How does heat affect this arrangement? Yes, Mariam?
As whenever we give heat, that the molecules, they will gain more energy, so they will move faster.
What energy will they gain? What sort of energy?
Heat energy.
Sorry?
They will take in more heat energy that will be turned into kinetic.
Very good. Very good. Yes. So their average kinetic energy will increase. Okay. Yes. Okay. And so is your answer complete? Yes. So yes, you are right. So as we are providing heat energy, the average kinetic energy of the particles will increase. And so then what would happen?
So they will move more faster. I mean,
Yes.
they're
Yes.
they will have more stronger repulsive forces from each other.
Okay. So
And
are you right now explaining a solid getting heated? Is this solid getting heated?
no, gas.
This is gas getting heated. Okay.
Yeah.
Yeah, it would be better if you start from solid. I want somebody to tell me in a smooth way, how does the heat affect the arrangement of the particles from solid to liquid to gas? Can anybody do that? Yes, Zores. Okay, Zores. Let me give a chance to Zores. Yes. Yes, Zores. Okay, Sarah.
Can I explain?
Okay, Sidra. Because I'm trying to unmute, but you guys are not getting. Okay, Sidra.
So if you apply heat to solid, so because you're applying heat, you are you're providing more kinetic energy to the particles, so they'll move more vigorously, and so the intermolecular forces will get weaker. So the particles will get more farther away from each other, and it might result in the solid turning into a liquid if you apply a lot of heat.
So yeah, so yes, you are right. So we are providing heat energy, and that heat energy is increasing the average kinetic energy of the particles. And so they are moving more violently. And if you keep providing energy, they will move so much, their movement would increase so much that a time would come that the intramolecular forces of attraction will weaken. You will not say broken. Okay, the word broken would be when you are explaining boiling. Yeah, liquid turning into a gas.
So then if you apply heat to liquid, then again the particles.
And so the arrangement, so you have to mention that the arrangement was regular. That regular arrangement is lost, and now the arrangement is just random. There is no particular arrangement.
Yeah.
And the particles are farther away from each other, and the intermolecular forces of attraction have weakened. So this is liquid state now. Okay. Now you keep providing heat.
So now if you keep providing heat, you already know that the intermolecular forces are already very weak. So if you keep providing heat, you're gonna provide a lot of kinetic energy to the particles. And so a time will come when the intermolecular forces will break.
Very good.
And when they break, now there is nothing to keep them together, so they will just go as far as they want to. So they will just like turn into a gas.
Yes. Yeah,
and that is like boiling.
Yes. So when the intermolecular forces of attraction are completely broken, now the particles are free to move, and so they will go as far away as is possible, right? Okay. So we have done this. Is there any question?
What will happen if you keep providing heat even when it's a gas? It will just keep getting further away.
Okay, repeat your question, please.
What will happen if you keep providing heat even when it's in gaseous state? Will they just keep getting farther away because now the intermolecular forces are broken?
So if you keep providing heat even when the substance has turned into a gas, you will only be able to increase their average kinetic energy. So their temperature will increase, and it depends upon if the gas is allowed to expand. If the gas is allowed to expand, it will expand. Okay. And if the gas is not allowed to expand, it is within a container that cannot increase in size, then the pressure will increase, and so on and so forth. Okay, so you are basically increasing the average kinetic energy. If you want to add something. Yes.
And if the gas is made up of a molecule, so if you keep providing energy, the molecule might break or degenerate.
Well, that you're going into a chemical change. then you're going into the chemical change. Okay, we will restrict ourselves to physical change. Okay, okay, but yes. Okay, so this is a graph of temperature against time. Temperature in degrees Celsius against time. Can you see it properly? Let me, okay, you remove these. Yeah. Okay.
Yes.
Yeah, okay. So this is temperature, this is time. So this is a curve for water. I won't tell you what curve, you will tell me. Is this a heating curve or a cooling curve? So what's happening? The temperature, I'm rising the temperature all the way from -10 to 0.
It's a
Yeah,
heating curve.
very good. Yeah, heating because I am increasing the temperature. If I'm increasing the temperature, the curve will be called a heating curve. Okay, so the temperature is rising all the way from -10 to 0. 0 is the melting point. Okay, and then, okay, who will explain this? Who will explain this graph? Aisha?
Yes.
Yes, can you please explain this graph to us? Heating curve of water.
From -10 to 0, it
Yes.
is melting.
Okay,
And
what is A?
A is when it is a solid.
Yes, so solid of water is called?
Ice.
Ice. Okay, now so you are increasing the temperature of ice
to 0, and at that time it's a liquid, and B is a liquid.
B is a liquid?
Yes.
Confirm?
Yes.
Okay, then?
And then all the way from B to C, all the way through C, it is evaporating.
C is evaporating?
It's boiling.
It's boiling?
Yes.
No, teacher, isn't it boiling from E or D?
Yes, Sabiha? Sabiha, what are you saying?
Isn't it boiling at 100 degrees Celsius?
Very good. Yes. Yes, Sabiha, you are right. So Sabiha, can you continue from here? B. What is B?
Water.
Water. Okay, Zores. Yes. Yes, Zores.
No, hello?
Yes.
A is the point where there's ice. B is the point where ice starts forming. C is the point where it's going to evaporate. D is the point when it's boiling, and E is the point when it's D is the point where it starts boiling, and E is the point which it starts boiling violently.
Okay. Okay, Ajwa. Yes, Ajwa.
B is where it is melting, and there is solid plus liquid at this point.
Yes. Yes. This is solid plus liquid. So you will see ice melting. So you will see ice plus water. Okay, good. C is?
C is liquid water.
Yeah, this is purely liquid. Okay, because all the ice has melted. Okay, now remember this. Here at this point, all the solid has turned into liquid. Okay, so here you have only solid. I mean, at this point, before the flat portion of the graph, you have solid, only solid. Now, from where you start having a flat curve, that's where you have both solid and liquid. You will see a block of ice with a puddle of water at the bottom. You will see a block of ice with a puddle of water. That shows that ice is melting. Okay. Now here, the whole thing. Now here, the temperature will never rise until all the ice has turned into a liquid. This graph will never rise. Okay. If you still see ice, if you still see solid, that means the temperature has not started rising. The temperature will rise only and only when all the ice has melted into liquid. Yes, Ajwa, please continue. After C, so C is only liquid, pure liquid, 100%. Okay, then?
Then at D, we have boiling, which has liquid plus gas.
Yes, again, we have liquid plus gas. The temperature will never rise until and unless all the liquid has turned into a gas. Okay, until and unless all the liquid has turned into a gas. So here you will see both liquid and gas. You will see liquid plus gas. Okay, then this is?
At E, it is gas.
The simple gas, 100% gas. And so we are still heating. So again, we are increasing the average kinetic energy of gas. Okay, okay, so this is called the heating curve of water. Now, another question. This is for grade 8 and 9 students. Why is it that this, well, grade 6 students, if they can answer, they are also most welcome. Okay, so why is it that the plateau of this curve is bigger at the boiling part compared to the melting part? Why is this longer? My question in simple words is, why is this plateau longer than this plateau? So we can see that there are two plateaus, right? Two flat parts. Plateau is flat part, okay? So my question is, why is this flat part longer than this flat part? Yes, Sarah?
Because melting requires less temperature, and so it will take less time compared to boiling. Boiling requires increased temperature, and so it will take long.
So why does boiling require more energy? Okay, don't say temperature, okay? Don't say that boiling requires more temperature. You will say that boiling requires more energy. Boiling requires more energy as compared to melting. So now tell me why. Why does boiling require more energy?
Because the molecules have to break free of the intermolecular forces in the liquid.
Okay. Okay. And so compare it now with melting. Compare it now with melting. Yes, that's correct.
And melting, it doesn't. It just flows instead of breaking free. Like the forces of the intermolecular forces are becoming weaker.
Yes.
Instead
Yes.
of just disappearing.
No. Yes, you said the words, but make a correlation. Now listen to this explanation carefully, okay? I want you to tell me in the same words. I mean, I want you to tell me the same points. Boiling requires more energy. Yes, that is correct compared to melting. Reason being, in melting, what's happening? Only weakening of the intramolecular forces. That's it. Okay, the space between the molecules is increasing, but not as much as compared to the gases. Have you seen? I mean, the gas particles are really far away. Okay, also in boiling, the intramolecular forces of attraction need to be completely broken, whereas in melting, the intramolecular forces only need to weaken. They are not broken completely. Here they have to be broken completely. Here they only weaken. Secondly, the molecules don't go too far from each other in melting. Yes, they go far, but not too far. In gases, they go really far, as much as the space allows them. Okay, so these are the 2 points. So what were the 2 points? One was complete breaking of intramolecular forces. Incomplete breaking, I mean weakening. You will use the word weakening, not incomplete, okay? And you will say that the molecules go farther away. Here, they don't go too far, okay? Third point is that here, the molecules even have to work to rise from the liquid surface and rise into the surrounding air. The molecules have to work, you know. Now, for example, if this is a liquid, the molecule, if for example, this is a molecule and it has now enough energy to break the intramolecular forces, it has broken the intramolecular forces completely. And so it will now need work. It will need to do work to rise out, to rise up. So all this requires a lot of energy. Okay, all this requires a lot of energy. It is working, it is moving. It requires more energy to do that. Okay, whereas from solid to liquid, the particles are still there. It's only weakening and they're not going too far from each other. Okay, so this is easy to understand. So melting requires less energy as compared to boiling. Boiling requires more energy, and therefore boiling takes longer as compared to melting. So melting is faster, boiling is longer. Okay? Okay. So now let's look at the cooling curve. Why am I calling it a cooling curve of water? Because now I am decreasing the temperature all the way from 140 degrees Celsius to negative something, negative, let's suppose 10. Yes, Sidra? Yes. Come and please speak louder.
Is evaporating also as
Evaporation.
Is evaporation also as hard as boiling? Like, does it also require a lot of energy?
Yes, it does require energy, but it's a slow process, whereas boiling
But it still also needs to break the intermolecular forces.
Yes. So the difference between boiling and evaporation is that boiling takes place at the boiling point, okay, of that substance, whereas evaporation can take place at any temperature as long as the substance is in the liquid form. Yes, Santos, you want to say something? You want to add something? Okay, so this is there any question from, yes, Zores? Yes, Zores?
No, teacher, I just forgot to lower my hand.
Oh, okay. If there's any question, please, you're most welcome to ask.
No, teacher, I don't have any question.
Okay.
Miss, I have one question.
Yes.
What if we put the temperature to 200 degrees Celsius?
Okay. So
then what will happen? So won't the evaporation be faster then?
yes, of course. So, you know, when you are at 200 degrees, I mean, if you're talking about water, so 100 degrees Celsius is the boiling point, right? So that means all the water has boiled. Now, all you are left with are water vapors or steam, right? You keep heating that steam all the way till 200 degrees Celsius. It will stay steam. It will stay steam, but of course you are increasing the gas will expand if it is allowed to expand, as I just mentioned. And if you are not allowing the gas to expand, the pressure will increase. Why will the pressure increase? Who will tell me? Why will the pressure increase? Yes, Abiha, very good.
I actually raised my hand because I have a question.
Okay, but can somebody answer my question first? Because I don't want to forget this question then. So if we don't allow the gas to expand and if we keep heating it, the pressure will increase. Yes.
Because you are just increasing the temperature and not letting it escape. So there's more pressure per unit area. That
pressure per unit area?
Sorry, force per unit area.
Yes.
That means the particles are colliding with much more force because you have increased their kinetic energy. Whereas when the temperature was less, so they were colliding with the walls, but not with too much force. And pressure is force per unit area. So because you are increasing the temperature, there's more force per unit area. So pressure increases.
Very good. Yes. Yes, Javeria. Yes, Javeria, you want to explain? Okay, Sabiha, now you ask.
Gas can turn into a liquid, right, by condensation or something?
Yes,
So does the condensation also happen at 100 degrees Celsius?
Very good. Yes, yes. Condensation also takes place at 100 degrees Celsius. And in fact, I was about to ask somebody to tell me, explain this cooling curve now. So Sabiha, you want to do that?
I'll try.
Okay. I like your participation. You know, Sabiha is a 6th grader. Yeah, and she's participating really well. Okay. Tell
At
me now.
A is a gas.
A is a gas. Very good. Why?
And
How do we know? How do we know that it's a gas? Why did you call it a gas? Because
it's the
because
number
yes.
is bigger than 100 degrees Celsius.
Yeah, because the temperature is higher than 100 degrees Celsius, and we know that a boiling point of water is 100 degrees Celsius. Any temperature above 100 degrees Celsius, the water will be in the gaseous state.
In 100, and then in 100 B in 100 degrees Celsius is condensation is going to happen, so it's going to be a gas plus liquid.
Very good. Yes, you learned. Very good, Sabia. I like it. Yes. So you have learned. So now you know that whenever you have a flat in the curve, in heating or cooling curve, remember you have 2 states of matter. One is the state which is before it, and the other state which is after it, because there is change of a state going on in this. So yes, so which 2 states will you have here in condensation?
Gas plus liquid and gas and liquid.
Very good.
And then
now see, she is a 6th grader, and in the heating curve she was making a mistake, and now she has corrected her mistake. This is what I like. Okay, then go on. What is C?
It's going to be a pure liquid.
Very good. This is pure liquid. Okay. Okay.
And then D
so again, now we have a flat part.
Liquid is going to turn into a solid.
Very good. So what 2 states will be here?
Liquid plus solid, liquid and solid.
Very good. Liquid plus solid. Very good. And E would
be a pure solid. It will be a solid.
Very good. This will be pure solid. And so what is this process called? This was condensation, and this would be?
Sublimation.
No. See, liquid turning into solid is what?
Freezing.
Right. Very good. Yes, freezing. In which grade are you?
Grade 6C.
So how do you know sublimation?
I learned about it in physics.
You read about it in physics. I don't think it is in physics, is it? I mean, not in grade 6. Okay, so tell me, what do you know about sublimation?
Sublimation is when a gas turns into a solid.
Yeah, when a gas turns into a solid, or solid turns into a gas without passing through liquid state, right? A direct jump. A direct jump. Yes, that is sublimation. Okay. What are the substances that undergo sublimation? Do you remember any?
Yes.
Yes.
Carbon dioxide and iodine.
Very good. And there was a third one.
No, those are the only.
Ammonium chloride. Not ammonia, ammonium chloride. Yeah. Okay. Okay. So now you understand this cooling curve. Okay. Is there any question regarding this?
No.
Okay. Abdul Rahman Saqib, did you understand this?
Yes, miss.
Okay, good. Okay. Now let's move on. Okay. Now let me talk about the potassium. Okay, I will talk about this potassium permanganate crystal diffusion. Okay, what is this? Potassium permanganate crystal diffusion. Okay. Your biology for you has a diagram for it, right? Do you have it? Can you please take that diagram out? So now, why did we use potassium permanganate crystals? Anybody? Any idea?
Yes, because it has
Because they can diffuse in water,
In water.
and
What
we can absorb the diffusion
because they
over
have
time.
you can easily see them and they're visible.
Yes, very good, Javeria. Yes, that's right. Because now potassium permanganate is itself is a solid, and so we will dissolve it in liquid in the solution form so that it can flow, right? Right. No, I want that. Okay, just leave it. Okay, so yes, so it is a solid. Can you see the picture? Okay.
Sure.
Yes. Okay, so it's a solid, so we will dissolve it in liquid. Okay, so that because of the random and constant motion of the fluid, which is water in this case, the diffusion would be made possible. If you don't dissolve this solid in liquid, of course, this is solid, and so the particles will not move. Okay, so if you leave it, and remember, we will introduce this very peacefully, meaning without disturbing the water, because if you disturb the water, that would be called stirring. That means you stirred the water. That means you applied external force. Then it will no longer be diffusion. It would be stirring. Okay, so they use some sort of a straw, or they use some sort of spatula to make sure that they are introducing this crystal real peacefully to the bottom of the test tube, and then they will leave it undisturbed, absolutely undisturbed. And then after a few hours, you will see that this crystal particles would have diffused. Now at this point, you can see that there are more, the bottom of the test tube is darker as compared to the top half. Why? Because diffusion is going on, but it hasn't completed. You still have higher concentration at the bottom as compared to the top. But after a few more hours, you will see that now the color is uniform. So the particles kept diffusing till the concentration is uniform throughout. Now the top and the bottom are the same color, okay, because same concentration. The reason why we chose potassium permanganate crystal is because it is so brightly and dark colored, it's easy to observe. Well, we can use any other crystal provided it is soluble, first of all. Secondly, it should be brightly colored. Okay. Now, why do we want soluble? Because if, for example, we used sand, let's suppose. Now, sand does not dissolve in water.
So it will never diffuse because it's not.
And does not dissolve in water because it's insoluble.
Right. Why is it insoluble, Sidra?
Because the particles of the sand are like too big, they're too coarse, it's very coarse.
Yeah.
And so they will not fit between the intermolecular.
Right, because the sand particles are too big to adjust in between the water molecules. The intramolecular space in the water is not enough to accommodate big sand particles. So, dissolving is the solute particles accommodating. This is dissolving. They have, yeah, this is very good diagram for dissolving. See, for example, this is the potassium permanganate crystals, a clump, for example, a cluster or a clump of particles in the center. And now they are distributing uniformly throughout. And now you can see that they have dispersed uniformly throughout. Now you cannot say that the right half of the dish has more molecules than the left, or the top has more than the bottom, or vice versa. Throughout, you have uniform distribution of the crystal molecules. Okay, so this is called diffusion. So that also tells us that solubility is one of the factors that is affecting diffusion, right? So if the solvent is dissolving the solute will diffuse easily. So solubility is one of the factors that will affect the diffusion, right? If a solvent is not dissolving the solute, the diffusion will not take place. What are the other factors that might affect the diffusion, the rate of diffusion? Yes,
Temperature.
Very good. Yes, please raise your hand. Okay, please raise your hand. Yes, temperature. Yes, Aisha.
I have a question.
Yes.
It's not called diffusion if an external force is applied, so how can temperature change the rate of diffusion? Because it's no longer diffusion.
See, when we are increasing the temperature, we are increasing the energy of the particles. We are not like physically moving the particles themselves. But yes, we are increasing their average kinetic energy. And so with that kinetic energy, the rate of diffusion increases. Okay. So it is their own energy, which we provided. But yes, we did not physically move them ourselves. By external, I mean to say that, the molecules should not be physically moved by something, Did you understand me?
Yes.
Yes. Okay. So what other factors? So yes, temperature is one. So how does temperature influence the rate of diffusion? And what do we understand by rate? Rate means how fast in per unit time. Per unit time. Okay. What are the other factors? Yes, Aisha?
I wanted to answer the other ones. That how does it affect diffusion?
Okay. Okay.
So when you provide a solid heat, there's more kinetic energy, and some spaces are created between the
When you
molecules.
provide a solid heat, did you say solid?
Yes.
Diffusion does not take place in solids.
Sorry. When you provide heat to a liquid, the
To a fluid,
molecules
you can say a fluid.
to a
Okay, so
fluid,
that will include both gas and liquid. Okay.
the molecules move faster, and if it's a liquid, the intermolecular forces are broken, so there's more space between them, and
You are now confusing with the change of a state from liquid to gas. You're explaining me the state of change from liquid to gas. Just explain me diffusion.
so there are spaces created between the molecules, and so more solute can be dissolved into the solvent.
Okay. Okay.
Yeah, I know another factor that affects the rate of diffusion.
Okay.
Concentration gradient.
Yeah, but let's talk about temperature first. So yes, Aisha, you explained very nicely. Yes, it does increase the intramolecular spaces of the solvent, but also talk about the average kinetic energy increasing of the solute, because of which it is able to move faster and it is able to move farther. Okay, that's very important. So you talked about the intramolecular spaces of the solvent increasing. That's a secondary point that will come later. First, you will talk about, you see, you are talking in terms of solution only. But what if the substance is pure? There is no solvent to dissolve into. Okay, so then that point would not be valid for that answer. So you talk about the average kinetic energy of the solute particles increasing, which will enable them to move faster and farther. Okay, and yes, even if we're talking about pure substance, it is always one substance diffusing into another. It is like that. For example, look at this. For example, this is the diffusion of iodine gas. Right? Now, initially the iodine gas was in this cylinder, okay? But when we covered it with another cylinder upside down, now the iodine gas is diffused because now the space available to it doubled up, and now it has double the space available to it. And now the diffusion will continue until the concentration of iodine molecules is the same in both the cylinders, all the way from top to the bottom. Okay, so now again, what's happening here? Now you have bromine particles, and then you have air molecules as well, right? For example, you have bromine particles here, but then you have air particles here, right? This is not a vacuum, right? This is air molecules. Okay, so again, you have two different types of molecules, and so both of them are diffusing, by the way. Both of them are diffusing. Bromine, there will be net movement upwards. And for air molecules, the net movement would be downwards because both of them are moving from their regions of high concentration to their regions of low concentration. Air molecule is also moving from their region of high concentration to their region of low concentration, because here there will be more iodine molecules than air molecules. Remember, molecules diffuse down their concentration gradient. Now, what is a concentration gradient? What is concentration gradient? Yes, Sidra?
It's
Please come closer and
it's
be louder.
like a difference
In the concentration.
in the concentration.
Yes. Okay. So it's like, think of it as
It can be difference in anything.
yeah, think of it as a difference in the levels of two floors, and so you have a staircase. Okay, so the more the difference, the faster you can fall. Okay, the faster you can fall. Okay, so more the concentration gradient, faster will be the diffusion. More the difference in their concentration, faster will be the diffusion. Remember this. So yes, it is temperature, solubility of one molecule into another. Yes. And third, you said concentration gradient. These are all factors which affect the rate of diffusion. And what else? Yes, Sabiha, what other factor? Yes. Can you unmute yourself? Yes, Sabiha, you want to add any other factor? No? What about the molecular mass? What about the molecular mass? मोटे लोग तो ज्यादा हिल नहीं सकते ना, मोटे लोग तो ज्यादा चल नहीं सकते, right? So the bigger the molecule, the harder it will be for the molecule to move, right? A bigger a molecule, the harder the harder will be for it to move. So if there's a big particle, it will diffuse slower. If there's a small particle, it can go farther. It will be faster. Small molecules will be faster as compared to big molecules, just like, you know, us humans, or, you know, big things, their movement is difficult, right? Okay, what other factor? What other factor? Distance traveled. Distance traveled. How far away the molecule is from its source. Okay, if the molecule is too far from its source, like for example, if somebody is wearing a perfume, and if the perfume is too strong and the person is, you know, loaded with perfume, well, you can smell that person within that room, or if the room is too big, you can smell that person till the you know, the other side of the room. But can you smell that person outside the house? No. It would be hard. Or maybe outside of the, you know, street, it would be hard. Why? Because the distance from the source is too much. Now the diffusion, so diffusion has a limit to it. Okay, there will be limit to till where the molecules. Why? Because the molecules will lose their energy as they will go farther and farther away from the source. The molecules will lose their energy, and so once they have lost their energy, they will no longer diffuse. Okay, so there is a limit to till where diffusion can take place. Okay, now I will talk about, yes, is there a question?
Even surface area affects diffusion.
Surface area. Well, yes, if you know there's if there's diffusion taking place between two surfaces, between two substances which are in contact with each other, if the movement is across a surface, then yes, surface area would be important. But if it is not across a surface, then surface area will not be involved. Okay, Is there any other question? Yes, Javeria? Oh, sorry. Yes?
Does pressure affect the rate of diffusion?
Well, yes, it might affect. You see, pressure is trying to bring the molecules together. Okay, so if you are applying pressure in such a way that you are squeezing them together rather than allowing them to spread as far away as possible, then of course you are preventing diffusion. The rate of diffusion will be affected. You are preventing diffusion. Okay. Okay. Now, okay, I'm just taking 15 more minutes. Okay, I'm sorry. I know Isha Salah has been called. Those of you want to offer Salah, they are free to leave and they can watch the recording. But I want to wrap up Brownian motion as well. Okay, now Brownian motion is due to random constant motion of the particles, right? We all know. Now, again, Brownian motion can only be observed in fluids, liquids, and gases. And again, constant random motion. So this is another evidence of our kinetic model of matter to be true. This is an evidence that our kinetic model of matter is true. So the particles, the substance is, so this shows that substance is made up of small particles, right? Which was the first point of kinetic model of matter. And the other thing is that they are in constant random motion, as you can see with the help of these arrows, right? Now, because the molecules are so small and we cannot visualize them, therefore, the scientists use smoke particles or pollen grains if we're using a liquid solution, or smoke particles if you're observing gas particles. Okay, because the smoke particles are big enough to be visualized, and we can use a microscope to improve our vision. And under the microscope, we can see that there are small particles and they are, they have a zigzag motion. I mean, they have a random motion, they are colliding with each other and all of that. And I will show you the video. Okay. Have you ever seen a sunny window? Now, Sidra, I want to share the video. I want to show you a Brownian motion. I will share my screen. Have you ever observed your sunny window, and we know especially when the sun rays are entering through the window into your room and you dust particles? And now can I share from YouTube? I don't think I remember. No, from YouTube. अच्छा अभी तो ये दिखाओ चलो. Okay, slideshow. Close karo. Okay. And the camera should be off. No, I don't need the camera anymore. Okay, can you see the video?
Water can exist in 3 different states. In the iceberg, it's solid. In the sea, it's a liquid. In the surrounding air, it's a gas. Solid, liquid, and gas are the 3 states of matter. Solids have a definite shape. A block of ice takes the shape of its mold. As it melts, it changes. The water spreads out and fills up the container. All liquids behave this way. They flow and find their own level. Gases spread out even more, filling any space available. The way solids, liquids, and gases behave gives us clues about how their particles are arranged. In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. But how do we know the particles in a gas behave this way? Some of the evidence comes from looking at how smoke appears under a microscope. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light enables it to be viewed under a microscope. It looks like tiny jittering points of light. When a straw burns, the smoke produced is mostly bits of carbon which haven't combusted. Under a microscope, they catch the light and appear to glimmer. But why do they randomly dance around? The movement of the smoke is caused by collisions with invisible air particles. As the air particles move about, they knock the smoke first this way, then that. Particles in a gas move randomly and quickly. Flowers produce pollen, which is a very fine dust, easily brushed off
Yeah, but that's it. That's it.
by a finger.
Okay. So, okay. So, are you guys with me? Did you see the video?
Yes.
Okay. So now,
Yes.
yes. Okay. Yeah. Write down. Okay. So you saw the smoke particles which were bigger, and they were being bombarded by the air molecules, right? Let me show you. Yeah, I want to show you another video. No, wait. I'm sorry about this. Window dust particles. Sorry about this. Yes, this. Okay. Okay, so the reason why we use smoke particles is because they are big enough to be seen. So the reason why they move is because they are being bombarded and pushed around by these invisible small air molecules, right? So we cannot see the air molecules themselves, but we can see the smoke particles being pushed by them. So the scientists, they concluded by looking at this random motion of these smoke particles is that the air molecules do exist as small particles and they are in constant random motion. So this Brownian motion supported our kinetic model of matter. Now in exams, they do ask that what is the significance of this Brownian motion? First of all, they will ask you to draw the pathway of the molecule. And so you will draw this diagram, which is in your book. You will show them in all the different directions. Okay, and then secondly, they will ask you what you observed. So you will say that the smoke particles are, in random motion. Yeah, this one, I think. Yeah. So they are in random motion. And then how does this support the kinetic model of matter? Okay, yes. Now, I also, this is very common when you see sun rays entering through your window into the room. You can see dust particles, right? Now I'm again sharing my, this is the last video. And after that, I will end the class. Just watch this video. In this video, you can see the dust particles moving in random motion. And that is because they are also being pushed by the invisible air molecules, right? But in this case, we don't have smoke particles, we have dust particles. The dust particles are big enough for us to be seen. And why are they moving this way? Because they are being bombarded by the air molecules, which are invisible. So I'm playing the video now. You must have seen this many times, especially in the morning and just before Maghrib. When the sun rays are slanting and are entering through the window, you can see dust particles in this motion. Okay, this is Brownian motion. This is nothing but Brownian motion. So why are the dust particles moving in this way? Because they are being bombarded by the air molecules. Tabiha, can you see?
Yes.
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 Yes. Have you seen this?
Yes, teacher.
Yes.
Yeah. So this is Brownian motion. Okay. Okay. So is there any question? Is there any question? Okay. I also wanted to. Okay, I also wanted to do a few MCQs with you regarding diffusion, but you know that we are out of time. So maybe next time. Yes, Ayan, you want to ask something?
Yes, miss.
Yes.
Miss, those dust particles were molecules?
No, beta, that's what I'm saying. The dust particles are being bombarded by air molecules. You know, the video that I showed you before, the first video, in that they showed you a model in which the bigger black smoke particles are being pushed around by the invisible air molecules. So because we cannot see the air molecules themselves, since they are so small, but smoke particles can easily be seen because they are bigger. So we know that there is no other reason for this random motion except for the fact that they are being pushed around by the invisible air molecules. Did you understand?
Yes, miss.
Okay. I saw another hand raised. Is there any other question?
No, miss.
Okay. Okay, then inshallah, see you tomorrow. Tomorrow I will take math class for grade 6. Okay, how to take out square roots and cube roots. Okay, inshallah. Okay, assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz, teacher.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.